Okay, now we'll see a fairly similar type of problem when we have a weak acid reacting with a strong base. We just need to be careful about Ka, Kb. Are we calculating hydronium? Are we calculating hydroxide? That sort of thing. So 20 mils of CH3CO2H, that would be acetic acid here. That's our weak acid. This is reacting with 20 milliliters of lithium hydroxide. So our first reaction is going to be that weak acid reacting with our strong base. Since we have a strong base involved, this is a one-way reaction. So moles is really all we need to figure out what's going on in the reaction. This is going to produce water in this case, since it's a hydroxide base, right? And a salt. In this case, it'll be the lithium salt of acetate, which is our conjugate base of the weak acid. So I'm just going to write those separately because I want to point out, right, what is it that we need to be worried about, what don't we need to be worried about. Lithium, being the conjugate in a sense of the strong base, doesn't have an effect on the pH of the solution. So we don't need to worry about how much lithium is around. But acetate here is the conjugate of the weak acid, so it in itself is a weak base. So we're going to have a concentration of weak base left over after this initial strong base reaction. So 20 mils, 1 molar, this is the same calculation we saw on the last page, actually a couple times on the last page. 1 mole per liter, 1,000 milliliters, so that is 0.02 moles. So there's 0.02 moles of the acetic acid and 0.02 moles of lithium hydroxide, so equivalent. And that means there's not going to be either of those left after this reaction happens. Right? We will end up with, so none of the products to start with, 0.02 moles of lithium cations and 0.02 moles of acetate ion after the reaction happens. Now again, we said lithium's not relevant to pH, but acetate is, and once we get into an ice chart, we're going to want concentration. So let's take that 0.02 mole, 20 mils of one liquid combining with 20 mils of the other is 40 milliliters or 0.04 liters. So this would again be 0.5 molar in terms of the concentration of acetate ion. And that gives us the second equation that we can think about here, and that is what happens when acetate ion reacts with water. Acetate is a weak base, it will deprotonate the water, and that will reform the weak acid, acetic acid, right? And that will leave us with some hydroxide ion in solution. Now, the important thing to recognize here, or there's plenty of important things, the next important thing to recognize here, this is a base reaction. We were not given a Kb, we were given a Ka. So we were given Ka for acetic acid. We actually need the Kb for acetate here. So here's where we're going to use Kw to solve for what Kb we actually need. Let me move that up here, see how much room you have left on your paper. Ka times Kb is equal to Kw. If we need Kb, we can divide through by Ka. Isolate Kb on one side. Kw is 1 times 10 to the minus 14th. We're given the Ka, 1.8 times 10 to the minus 5th. So Kb here for acetate ion is 5.56 times 10 to the minus 10th. Okay, so it's actually 5.5 repeating, right? But I'm going to keep a little extra data there just to limit rounding errors in my answers. It should really be 2 sig figs, but I'm going to keep it as 5.6 instead of 5.6. Okay, got Kb here. Now we can think about the ice chart, right, to start to figure out what's going to be going on at equilibrium. If we start with 0.5 and there's no products yet initially, that means we're going to lose some of our reactant, gain some of our products. At equilibrium, we'd have 0.5 minus x and x. Now, this x, can we eliminate this x here, this change? Right? This would be where we want to compare our concentration to our equilibrium constant, right? Our concentration of our acetic acid to the Kb that we're looking at. That would be 0.5 over 5.56 times 10 to the minus 10th, right? Now, top is kind of 10 to the minus 1, bottom is kind of 10 to the minus 10th. This is about 9 orders of magnitude difference, which is about 1 billion times different. So yes, this is fine. We can remove those minus x's. They're going to be, x is going to be pretty small compared to 0.5. Subtracting it from 0.5 won't make much of a difference. So that simplifies the rest of the problem. We can take our Kb, right, and we know how to write the Kb expression at this point, products over reactants. So the two products are x, so that would be x squared over the one reactant that would be in there is 0.5. That is fairly straightforward from a math perspective. 5.56 times 10 to the minus 10th, multiply through by 0.5, and then take the square root of both sides, and we end up with x is equal to 1.7. Now let me keep an extra digit there, 1.67 times 10 to the minus 5th molar. Again, what we were looking for here, I actually never really specified what we were looking for, I suppose, in these problems, but it's the pH of the solution, right? Now in this case, that's hydroxide ion, right? So keep in mind what equilibrium you're looking at. You can't always just go straight into negative log, right? You may have that extra step. So we can here go to POH. So if I do take the negative log of my previous answer, the concentration of hydroxide ions, the POH here is 4.78, right? And that to get to pH, we need to subtract that from 14. So minus 14, that would be 9.22 for the pH of that solution. This last step can be pretty important, right? If you forget that you're looking at a base instead of an acid, you might claim your pH is below 5, which really doesn't match with a solution that contains a weak base. It should be above 7. So try to keep track of that, right? Now, if you have your ice chart, that's a good thing to refer back to make sure. Okay, excuse me. One more example problem here on the page, right? And we've kind of gone through all the material in this chapter. There is another chapter of equilibrium coming up, but we've pretty much seen it all. So the last few here are just going to be some additional practice problems. So hypochlorous acid, HClO, we're given the Ka, acid dissociation constant. We want to calculate hydronium ion, hypochlorite, and hypochlorous acid concentrations at equilibrium given a certain initial concentration. So since we know this is a weak acid, we should be able to write out the reaction a weak acid would undergo. It would protonate the water, right? And that would leave the conjugate base, which is your hypochlorite ion. In our ice chart, we know the initial concentration, 0.009. Everything else would be 0. So as we approach equilibrium, we'll lose some of the reactant. We'll gain each of the products. Right? Now, that X, right? That X is what stands between us and maybe having to go through the quadratic equation. So we want to do this evaluation. Can we forget about the minus x here? Now, pretty low concentration compared to some of the other calculations we've been doing. So let me take that concentration and divide by the Ka. So Ka here is pretty small as well, times 10 to the minus 8th. So 0.009 divided by 3 times 10 to the minus 8th. And this comes out to be 300,000. So this assumption is very good. We can just remove that x. So that, again, that when we can do that, that makes this problem quite a bit easier. So I think it's more difficult in the beginning, right? You're not given the equation, you've got to kind of decipher what's going to happen, right? But if you can make that assumption, the math does simplify quite a bit. So products over reactants, so that's going to be x squared over 0.009. From there, we can solve for x. So 3 times 10 to the minus 8th, multiply through by 0.009, right? And then take the square root of both sides. And x is 1.64 times 10 to the minus 5th. That's going to be a molarity, right? Now, in this case, we were asked for concentrations. We weren't asked for the pH. Excuse me again. So you kind of get in the habit of just turning that answer into pH or POH, but be careful, make sure you read through the problem, right? In this case, X is both of the products. So the hydronium ion concentration here is 1.6 times 10 to the minus 5th, right? And it should really be 2 sig figs based on both our concentration we started with and the Ka value. The concentration of hypochlorite is also 1.6 times 10 to the minus 5th molar. Right? And then the concentration of the hypochlorous acid that we started with, and we have to take 0.009 and subtract 1.6 times 10 to the minus 5th. And that is 8 point, nope. If I'm only going to 2 significant figures, it is still 0.0090 molar. Right? So it does change a little bit here, but to 2 significant figures, it is still exactly the same. So this is a good indication of, yeah, our assumption is fine here because to the number of significant figures we have, this value doesn't change. So those would be our answers for that problem.